Heyo, it's Mr. Otwell, the Math Master, helping you master math. And today we're going to be looking at some examples of simplifying radical expressions. So in my last video, I talked about just properties of how radicals simplify. So you can go check that out. I'll leave a link to the description down below so you can click that. Off to the side here, I have some notes from that last video listed so that we can just reference those as we go. It's really going to help us to take care of these examples if we have some other properties to keep in mind, as well as just a list of perfect squares and perfect cubes. So what are perfect squares? Perfect squares are all these numbers right here. These are all numbers that there exists some other integer that you can square to get it. Okay, these numbers are called perfect squares because, for example, 2 squared is 4, so 4 is a perfect square. 6 squared is 36, so 36 is a perfect square, etc. These numbers here are called perfect cubes. These numbers right here, these are perfect cubes because there exists some integer we can cube to get it. 2 to the third power is 8, so 8 is a perfect cube. 5 to the third power is 125, so 125 is a perfect cube. We need these numbers because they will make our life better when we're simplifying radicals. There's many different ways to simplify radical expressions. One way is to do a prime factor tree. I will show you one example of that, but I also just want to show you another method that I think really kind of makes this process a lot quicker, especially when we start getting into much bigger numbers. So let's do this. First, let's talk about how you would simplify radical expressions using a factor tree, a prime factor tree. So factors are two numbers we multiply together that gets us another number. A prime factor is just a factor that's a prime number. Remember, prime numbers only have two factors, one and itself. So if we wanted to make what we call a factor tree, a prime factor tree, we would take 24, or whatever is under our radical, and split it up into two factors. And we would just start with, the smallest prime number we can think of, which would be 2. And we say 2 times what gets us 24? Well, we know that 2 times 12 gets 24. So we just keep going, though. 2 is a prime number, so we're good there. We would go to 12 and split that into prime factors. 12 can be split into factors of 2 times 6. So we can keep going, right? 6 also has a prime factor, 2. So 2 times 3 gets us 6. So once you have all your factors here listed that are all prime numbers, you're finished. At this point, you take a look at your index. Remember, if we don't have an index, right, what is it? It's a 2. We're lazy. We know there's a 2 there. We just don't write it because we're mathematicians. We're lazy. We don't want to write stuff if we don't have to. So the index tells us what we're looking for. The index tells us how many of the same prime factors we need in order to take those together and simplify them outside of the radical. So for example, we have 2 2's right here. So we can take 1 2 and pull it outside of the radical. These kind of just get squished into one number and you write them outside the radical. And then we just have a 2 and a 3 left. There's not 2 of the same number anymore. So these numbers are just left inside the radical. So you still have 2 times 3 in here. And you want to go ahead and multiply them because you know what 2 times 3 is. So you bring down the 2 that's outside the radical, and then you multiply what's inside the radical. And 2 square root of 6 is our solution. Square root of 24 is the same as 2 square root of 6. They're the exact same number. If you typed this into a calculator and this into the calculator, you get the exact same approximated number. This is just what we would call the simplified version of it. So I want to show you another way to do these that really I feel is getting at the heart of why all of this prime factor tree method works, as well as it just saves you time, okay? Really do whatever way works for you. Do whatever way saves you the most time. If you can really think through this next method that I'm going to show, though, and feel more comfortable with it, it will save you time, I'm telling you. So let's check that out. So we have the square root of 24, and we need to simplify it. Another way that we can think about simplifying radicals is looking not for prime factors, but in this case, because we have a square root, we want perfect square factors. Because if we get a perfect square factor, we know what the square root is. Okay, so for example, we have the number 24 here. If we just listed all the factors of 24, if we find one of these numbers here, because all these numbers, 1, 2, 3, 4, 6, 8, 12, 24, these are all the factors of 24. If one of these factors is a perfect square, then we're in business, because we can break 24 into separate factors, and then we will have this amazing perfect square underneath our square root, and it'll just go away. The radical will go away. It will simplify because we'll know what that number is. So from this list of factors, we can see that 4 is a perfect square factor. We know that the square root of 24 is the exact same as the square root of 4 times 6. So this is nice because we have this property right here, the product property. Okay, if we have two factors inside a square root, we can break them into separate square roots, which is nice because check it. We can make square root of 4 its own little factor here because 4 is a factor inside the radical, and then we can give the square root of 6 its own radical because it's the other factor. And check it. Oh, what's the square root of 4? We know that one is 2, right? Do we know the square root of 6? It's an irrational number, so there's nothing else we can do to simplify it. If this gave us some sort of factor that we could do the exact same process again, split it into factors where we know the perfect square, we would keep doing that. But we can't. Like, this is as simple as it gets. So the square root of 4 just becomes 2, and we just leave the square root of 6. And it's the same answer. So right now you might be like, hey, Mr. Otwell, your way's cool, I guess, but I like the prime factor tree. I'm just telling you, the reason you like it probably is because you've done this before, right? You've done this method before, so you're more comfortable with it. But if you put some time into practicing this method, I guarantee you, really the concepts of what's happening in simplifying radicals will make more sense, as well as it will save you time, okay? So let's check out another example, and we're going to stick with this method, all right? So now what if we have the cubed root of 24? Well, in this example, we looked for perfect square factors because it was a square root, but now we have a cubed root. So what are we going to be looking for? Do we want perfect squares? We want perfect cubes. We want perfect cubes because the index will tell us what to look for. So remember, looking over here, I've written some perfect cubes so that we can reference these different numbers. Because if we can find factors that are perfect cubes, we're in business, right? I already have the factors of 24 here, and you'll notice that the first perfect cube here, 8, is right here. So let's rewrite 24 as 8 times 3. Do you agree with me, right? The cube root of 24 is the same as the cube root of 8 times 3. 8 times 3 is 24. So all I did was just rewrite this expression in the same exact way. Now, why would I want to do this? Well, because we know this property right here. We can split this up to where the factor of 8 and the factor of 3 are in their own cube roots. Notice that on this property, the product property, the index always stays the same. So here we started with the square root, we split them up into square roots. Okay, here we started with a cubed root, so when we split them up into two separate radicals, we leave that cubed root there. All right, then let's check it. What's the cubed root of 8? We know that if 2 cubed is 8, then the cubed root of 8 is 2. So this factor is equal to 2. Cubed root of 3. Is there anything else we can do? Is there any perfect cube factor of 3? No. So we just leave that inside the radical, and that's the answer. We're done. Now let's take a look at another example where we have a variable in the radicand as well as a negative factor in the radicand. Really, the idea is going to be the same. We're going to treat these factors here, negative 16 and x cubed, as two separate things. Let's deal with the number first, then we can deal with our variable, okay? We're going to look for perfect cube factors, right? Why? Because we are dealing with the cubed root. So we want perfect cube factors of 16. Well, we know that 8 times 2 gives us 16. So we want to rewrite the cubed root of negative 16 as the cubed root of negative 8 times 2. Now, I put the negative with the 8 for a reason. Normally, when we're simplifying radicals, if we have a negative under the radical, we will simplify the negative outside of the radical. We don't leave it inside. You might be thinking, wait, Mr. Otwell, I thought that we couldn't have a negative in the radical. Well, if you check back my other video, I'll explain more of why that's true. But just remember, if you have an odd index, negatives under the radical are totally fine. So we want our negative with our perfect cube factor, because what is the cubed root of negative 8? Well, it's negative 2. And then the 2, we leave it inside the radical. Remember, if our index was a 3 here, we leave it as a 3 here. So the cubed root of 16 simplifies to negative 2 times cubed root of 2. But we still have this variable. Like, what the heck do we do with that? Well, I went ahead and simplified the cubed root of negative 16 here, but we know that this is also in the expression, right? We still have the cubed root of x cubed here. Now, what the heck do we do with that? Well, notice up here, we're still not changing. We want perfect cube factors. Now, what number, if you multiply it times itself 3 times, gets you x cubed? Well, x does. So over here with our perfect squares, I could add an additional little note here. If we add x squared, we get x squared. Okay, so x squared would be a perfect square because you can take x and raise it to the second power to get x squared. In the same idea, if you take x and you raise it to the third power, you get x cubed. So x cubed is also what we consider a perfect cube, because x to the third power is x cubed. We want to use this idea because we still want perfect cube factors. Now check it. We have x cubed here. So we know what the cubed root of x cubed will be. It would just be x. So this just simplifies to give us x here. Another way to think about it is checking out this. We had the b root of x to the b power gives us x if b is odd, and it gives us the absolute value of x if b is even. In this case, our b is 3, so it's odd. So we would just leave whatever the base is, that would be our solution. So it just comes back to this idea, right? The base of x cubed is x. So the cubed root of x to the third power is just x. Now, this is a weird way to write it. Like, we wouldn't ever write a factor outside of a radical times a factor inside a radical times some factor outside of the radical. We're going to go ahead and just move this in front. This would give us negative 2x cubed root of 2. And that would be our answer. Now, for this example, the square root of 50, x squared, we want to do the same idea. What are perfect square factors of 50? Well, we know that 25 is a perfect square, and 25 is a factor of 50. The square root of 50 times x squared could be just the square root of 25 times 2 times x squared, right? 25 times 2, same thing as 50, right? So we just rewrote this. We haven't changed anything yet. Why do we want to write it this way? Well, we know that we can use this property once again. We can break all the factors into their own little radical. So this would be the square root of 25 times the square root of 2 times the square root of x squared. Now, we know that the square root of 25 is just 5. Square root of 2, hey, there's no more perfect square factors here. So we just leave that as square root of 2. So here we have 5 square root of 2, but now we have to do the square root of x squared. So you might be like, oh, that's just x. But wait, just wait, right? You want to write x, you really do. But take a look at this. This is by definition how our radicals are simplifying whenever we have an index equal with the exponent of the radicand, okay? Notice, if b is even, The answer is the absolute value of x. So this is not just x, it is absolute value of x. So if we want to simplify really fully the square root of 50x squared, the answer, we would normally write our numbers first, our real numbers. So it'd be 5. Then we would write this factor here because it's outside the radical. So 5 times the absolute value of x, and then we still have square root of 2 here, and then we don't want to forget it, and we'll just add it right there. So the square root of 50x squared is 5 times absolute value of x times square root of 2. So now let's move myself over here. Okay, we made it. All right. I just needed some room right here, right? I got to have some more room here. So we have one last example here. We're going to kind of put it all together one more time. Let's do this. We have the cubed root of negative 54 times x to the 5th times y to the 6th. So you know the drill. We're looking for perfect cube factors because we have a cubed root, okay? So we can break all of these 3 factors into more factors. Do we have any perfect cube factors of negative 54? Well, take a look at our list here. Do we know 8 times anything? Does that give us 54? No. We'll just go to the next one. What about 27? 27 times something. Does that give us 54? Well, actually it does. 27 times 2 gives us 54. So we know 27 is a factor of 54, and we want that because we know what the cubed root of 27 is. It's 3. So this negative 54, we could just write it as negative 27 times 2, right? These are the same, but we still have x to the 5th and we still have y to the 6th power. Keep all that under the radical. So now, once again, don't forget that index, got to stay the same. Once again, we can take each factor that's under the radical and split it into separate factors. So let's just do that. So this gives us the cubed root of negative 27 times the cubed root of 2 times the cubed root of x to the 5th times the cubed root of y to the 6th. So we have the cubed root of negative 27. We know what the cubed root of 27 is. It's 3. But because we have that negative there, it's going to be negative 3. If you think about it, negative 3 times itself 3 times ends up giving you a negative number. That's why all this works out. But then we still have the cubed root of 2 here, right? Now, this is interesting, right? We have the cubed root of x to the 5th. So these numbers aren't the exact same. So what do? Well, once again, we can break x to the 5th into factors that are perfect cubes. So do you agree that this is the same? Right? I mean, x to the 3rd power times x squared, that is x to the 5th, right? Why would we do this? Well, we know what the cubed root of x cubed is. It's just x. Because the index matches the exponent, those will simplify. And we'll just have the 2 left over. But what about this cubed root of y to the 6th? Well, hey, y to the 6th is y to the 3rd times y to the 3rd. So we could write it like this, right? Y to the 3rd times y to the 3rd. Why is that helpful? Well, if we broke y to the 3rd into its own factors, right? Let's come down here. We have negative 3 times the cubed root of 2 times, let's just break these into separate radicals. The cubed root of x to the 3rd power times the cubed root of x squared times the cubed root of y cubed times the cubed root of y cubed. We're running out of room. We'll be okay here. Let's just scroll down here, give us a little more room. Negative 3 cubed root of 2 times cubed root of x cubed times the cubed root of x squared. Remember, we're just rewriting all of this. We're breaking them all into their own factors times the cubed root of y cubed times one more cubed root of y cubed. So here we already agreed we're good here. We don't have anything else to do here. So we'll just bring that down. We have negative 3 times the cubed root of 2. But what's the cubed root of x cubed? Well, that just gives us x. Remember, if the index is the same, it just cancels and gives us what the base is because b is odd. We can't do anything else with this. This is still the cubed root of x squared. We can't simplify this anymore. But we know the cubed root of y cubed. And we know the cubed root of y cubed, right? The same thing as this giving us just x. These two factors are going to simplify and just give us y. But there's two of them. We know what y times y is. Y times y is y squared. So if we want to take all this and simplify it, write it in one nice, beautiful expression, we would take everything outside of the radical, every single factor outside the radical, and put them in front on the left, and then everything that's left inside the radical, we will then put in the radical. So that gives us negative 3 x, because we have an x here, and then we have y times y, so that gives us y squared. And then we just have two more things that are inside the radical. So we're going to say the cubed root of 2x squared. So I hope that was helpful. If you have any other questions about simplifying radical expressions, go ahead and leave them down in the comment section. I'll get to them and help you out as much as I can. If this video is helpful, leave a like. Go ahead and hit that subscribe button. Show me some love. Mr. Otwell out. Peace.